Good morning students. Today we will discuss about Fermi-Dirac distribution or Fermi factor. So we can call it as Fermi-Dirac distribution function or Fermi function or Fermi factor. Now last class we have seen electrons. Electrons have half integral spins. Electrons are having half integral spins. So here electrons possess quantized energy states, means energy is quantized, and electrons obey Pauli's exclusion principle, that is the two electrons can exist in single state with opposite spins. Next, they satisfy Fermi-Dirac statistics. Here they obey Fermi-Dirac statistics. So, see here, now Fermi-Dirac distribution function, Fermi-Dirac distribution function, which is represented by f of E, is defined as the probability of electron occupation. Means here this distribution function gives the electrons occupying the single state. The electrons occupying single state. How many electrons are occupying single state? Which particle is occupying which state? That is given by Fermi-Dirac distribution function. Now Fermi-Dirac distribution function is given as f of E is equal to 1 by 1 divided by exponential E minus EF by KT plus 1. This is the Fermi-Dirac distribution function. This is equation number 1. Now, what is EF? EF is the Fermi energy. Means this is the energy possessed by Fermi level. So, EF is the Fermi energy which is possessed by Fermi energy level. K is the Boltzmann constant. Here K is the Boltzmann constant. Its value is given as 1.38 into 10 power minus 23 joule per Kelvin. Okay. Now, before going to this, you should understand how electrons are occupied in different states. Okay. Now, see here at T is equal to 0 Kelvin. At T is equal to 0 Kelvin. So, see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 levels. 10 levels. How many electrons are there? 20 electrons are there. 20 electrons are filled in 10 levels. How they are filled? 2 electrons in a state. 2 electrons in a state. So, what is the highest occupied level here? Which level is the highest occupied level? 10th level is the highest occupied level. This level we call it as Fermi energy level. This level we call it as Fermi energy level. So this we call it as Fermi energy level. The energy possessed by this level is called as Fermi energy. So Fermi energy is represented by EF. This is the state EF. Okay. So this is the Fermi energy EF. So this is the Fermi energy EF. Now, so see here, this is the case when you don't give any temperature. So, if I don't give any temperature, below EF, all states are, whether they are empty or completely filled. So, see here, we can see the diagram, they are completely filled. So, below EF, all states are completely filled. Above Fermi energy level, all states are completely empty. So, at T is equal to 0 Kelvin, all states below EF are completely filled and all states above EF are completely empty. So what is Fermi energy level? This is the topmost occupied level. This is the topmost occupied level. This is the topmost occupied level. Beyond that there is no occupied level. Next, see here, if I give temperature, T greater than 0 Kelvin, what happens when I give temperature? The electrons slowly move from this EF to other states. Next, electrons slowly move from one state to other state. The electrons move from one state to other state. The electrons move from one state to other states. Okay. So here electrons will be moving from lower energy levels to higher energy levels. So here below, see here above EF, Here this is the Fermi level, which is the highest occupied level in this diagram. This is the Fermi level because above EF, is there any, means here above EF all states are completely empty, but here I cannot find states empty. They are partially filled. So at T greater than 0 Kelvin, above EF, the states are not completely empty. They are partially filled. Okay, this we'll see now. This can be explained by the Fermi statistics or not, we'll see now. Okay, now we know Fermi Dirac distribution function. F of E is equal to, F of E is equal to 1 by E power E minus EF by KT, E minus EF by KT plus 1. This is equation number 1. Now we see this Fermi function, how it varies with respect to temperature. Okay. Now case 1. Case 1, at T is equal to 0 Kelvin. At T is equal to 0 Kelvin, if E is less than EF. If E is less than EF. So see here from the equation 1. Now from equation 1, what happens? F of E is equal to, so see here, E is less than EF. Means something less factor you are subtracting with more factor. What you will get? What you will get? Minus. So see here, we will get it as 1 by 1 plus E power minus. Okay. Now what is T? T is 0. So 1 by something. See here, this factor divided by 0 will be infinity. So I can write it as 1 by 1 plus E power minus infinity, which is equal to 1 by 1 plus 0. E power minus infinity is, E power minus infinity is 0. So I can substitute here 0. So what is F of E? F of E is 1. Means the probability is 100%. Means below EF, below Fermi level, below Fermi level means below EF, all states are, now see the diagram. So see here at T is equal to 0 Kelvin, below EF all states are completely filled or empty. They are completely filled. That's why you got probability 1. So below EF Fermi level all states are completely filled. Okay. So next, if E is greater than EF, if E is greater than EF, from equation 1. So if I substitute in equation 1, F of E is equal to, see here 1 by 1 plus E power, E is greater than EF. So I will get positive or negative? I will get positive. So positive. Next, here T is 0. So something divided by 0 is again infinity. So which is equal to 1 by 1 plus E power infinity. E power infinity is infinity. So I can write it as infinity. So F of E is equal to 1 by 1 plus infinity means 1 by 0. So if I take LCM, what happens? 0 plus 1, this to numerator, 0 by 0 plus 1, which is equal to 0. Means probability is becoming 0. Means above EF, means above Fermi level EF, all states are completely empty. Okay. So whatever I have discussed in the last diagram, all states below EF are completely filled and all states above EF are completely empty. So same result we got from this. Okay. Now Fermi level is defined as, how Fermi level is defined as? Fermi level is defined as the topmost occupied level. This is the topmost occupied level at absolute 0 temperature. Means at T is equal to 0 Kelvin, it is the topmost occupied level. Okay, now if I take case 2 at T greater than 0 Kelvin, if T is greater than 0 Kelvin, E is equal to EF. If I take E is equal to EF from equation 1. So what about equation 1? Now from equation 1, f of E is equal to 1 by 1 plus e power E minus EF. E is EF. So e power E minus EF by means 0 by kT, which is equal to 1 plus 1, 1 plus 1, 1 by 1 plus 1 divided by 2. Means the probability is 50%. Probability is 50%. Means it is neither completely filled nor it is completely empty. So now Fermi level is defined as, the Fermi level is defined as the probability of occupation is 50% or half at T greater than 0 Kelvin. So at T greater than 0 Kelvin, the probability of occupation is 50%. So here whatever we have shown in the diagram, we have proved. So above EF at T greater than 0 Kelvin, it is neither completely empty nor completely filled. Now we will see the variation of Fermi level. Okay, now we will see the variation of Fermi level. Variation of Fermi level with respect to temperature. We will see the variation of Fermi level with respect to temperature. So see here, variation of Fermi level with respect to temperature as a function of energy. So see here, the Fermi level, this is the Fermi level F of E, and this is the energy. The energy levels, this is the Fermi energy level. These are the energy levels below EF, and these are the energy levels above EF. So see here, F of E at T is equal to 0 Kelvin. What is the probability of occupation? Below, see here, E less than EF. These are the states E less than EF, and these are the states E greater than EF. So E less than EF, what is the probability I got? So see here, at E less than EF, what is the probability I got? 1. Okay. So the probability of occupation is 1. Next, at T greater than 0 Kelvin, what happens? T greater than 0 Kelvin. So see here, E less than, at T is equal to 0 Kelvin, what I have explained, E less than EF, the probability of occupation is 100%. 100% states are completely filled. And 100% above EF, all states are completely empty. That's why till here only I have drawn. Till this line, till here only I have drawn. It is completely filled. Next, at T greater than 0 Kelvin, the probability of occupation is 50%. 50% means neither below EF all states are completely filled, neither above EF all states are completely empty. So what happens? The electron will be moving from these levels to higher levels. Next, from these levels to again higher levels. Okay, so still more from these levels to higher levels. Next, from these levels to higher levels. So this is T1, T2, T3. We can write it as T3 is greater than, T2 is greater than T1. Means electrons move from these states to higher states. Again from other lower states to other higher states. Like that, this varies. So this is the variation of Fermi energy with respect to temperature. So this is about Fermi-Dirac distribution function or Fermi factor. Thank you.